I mentioned how the chain rule is really just going to be an expansion of existing derivative properties that we've already covered. So let's start by reviewing some of those different derivative properties we've established and get a better idea of what I'm talking about here. So we can start off with our theorem that we established for the power rule. So if we're taking the derivative of x to the nth power, that's going to be n times x to the n minus 1, so the original exponent comes down as that factor in front, and then times the derivative of x. So the derivative of x so far has always just been 1, so we tend to drop out that last piece, but when we originally introduced the theorem, that property, it had times the derivative of x there. Same thing for differentiating e to the x. This was the derivative of e to the x equals e to the x times the derivative of x and the derivative of the natural log of x gave us 1 over x times the derivative of x. So in each case, at the end here, we're always multiplying by the derivative of whatever that value was for x. For simple examples, when that's just x to some power, e to the x natural log of x, the derivative of x in each case is just 1, so those are pretty simple cases. So when we introduce these properties, we always included that derivative of x portion, which always equaled 1. We can still apply these rules exactly as they're written to composite functions without actually having to establish any new properties. So the only thing that's going to change is that that derivative of x at the end of each of those rules will be replaced with the derivative of the inner function if we're dealing with composite functions. So let's take a look at those 3 examples we introduced on the first page. We have the derivative, or we have the function x squared plus 4, that quantity being raised to the 3rd power. So we already established this is composed of u cubed and x squared plus 4. So if we want to evaluate the derivative of m, we would start off by taking the derivative of something raised to the 3rd power. So we have something in here being raised to the 3rd power. So that would be 3 times that inner function, x squared plus 4, squared. So that's just applying the power rule to this function. And then we're going to multiply by the derivative of that interior function. So this is exactly the power rule as we've always used it before. The only difference is instead of it just being x raised to some power, we have an inner function being raised to some power. So instead of multiplying by the derivative of x, we multiply by the derivative of that interior function. So this will become 3 times x squared plus 4, that quantity squared, times 2x, which is the derivative of x squared plus 4, which will give us 6x times x squared plus 4, that quantity squared. So now we've taken the derivative of a composite function without introducing any new properties or rules, just expanding on the ideas that we have established in previous sections. So when we look at the function e to the 0.04x, this again is composed of e to the u and 0.04x. So if we want to find y prime, the derivative of y, since e to the u is that outer function, we're going to take the derivative of this like it was just e to the x. So the derivative is going to be e to the 0.04x times then the derivative of 0.04x. So again, the exact same rule for differentiating exponents, except instead of e being raised to the x power, now it's being raised to some function, and then we take the derivative of that inner function. So this will just be 0.04 e to the 0.04x, because the derivative of 0.04x will just be 0.04. In our next equation, we have the square root of u and 4 minus x squared. So the first thing we want to pick up on is the fact that the square root of u is the same thing as u to the 1/2. So our outer function is just a power function. So to evaluate y prime, this is going to be 1/2 times the quantity 4 minus x squared, now raised to the negative 1/2 minus 1, so to the minus 1/2, times the derivative of 4 minus x squared. So this will give us 1/2 times 4 minus x squared to the negative 1/2 times negative 2x, or just negative x times 4 minus x squared to the negative 1/2. So again, no new theorems or properties are being established. We're just going back to sort of the more general version of each of these derivative properties that we had already established. In our last example here, we have natural log of 2x plus 3. So that outer function is the natural log of u. Inner function is 2x plus 3. So we're going to start off by taking the derivative using that natural log property. So y prime will equal 1 over 2x plus 3 times the derivative of 2x plus 3, which will give us 1 over 2x plus 3 times 2, or writing that a little bit more simply, 2 over 2x plus 3.